some sample problems for chapter 23. So you look at yourself in a mirror, so here's going to be a mirror being relatively close, and here's a mirror that's going to be relatively far away. Let's just kind of use ray diagrams to show that we're always going to see, the full length of our body. So angle of incidence must be equal to the angle of reflection, so that angle must be equal to that angle. Same is going to be true for right here. Now, if it's far away, simply going to have a different angle, so it's going to bounce off there. See your foot, kind of bounce off there, pretend I draw a straight line, and see the top of your head. And now some practice with ray tracing. Essentially, we're going to have a convex mirror, and so I'm going to make sure I draw my mirror like this, and I've written down the height of the object, the radius of curvature, distance of the object, and the focal length. So you say here, this is going to be my object. We always tend to draw these on the left hand side. So if this distance right here is 8, this distance would be about 16 centimeters. So I've drawn my focus on the other side here to be about where I think 8 centimeters ought to be. Now let's think about the lines that I need to draw. I'm going to draw a line that comes in parallel, and it's going to bounce off. It's going to bounce off like it goes through the focus on this side over here. Then I'm going to draw one that's going to hit right about there and bounce off at the same exact angle. So I'll kind of trace this guy back right there. Let it keep on going here. And then I'm going to draw one that goes through the center of curvature. I know the center of curvature is roughly 16 centimeters. So that's going to be my center of curvature. Kind of draw that one right there. It's going to bounce back directly to the very tippy top, and kind of imagine like it goes just like that. Where these three lines intersect, there's going to be my image, and it's going to be virtual. The reason for that is going to be light over here. My image is formed where there's going to be no light on this side. And since I didn't really do this to scale, I can't really make a good estimate of the image distance, except for to say, well, I expect it to be less than the 8 centimeters, maybe 5 centimeters or so. I also expect it to be smaller than my initial object over here. So now let's go ahead and calculate these guys out. I have one equation to use. 1 over distance to the object plus 1 over distance to the image is equal to 1 divided by the focal length. Focal length is negative because it's a diverging mirror, and so I'm interested in the distance to the image. So I'm going to say 1 over distance to the image is going to be 1 over the focal length minus 1 over the distance to the object. So that's going to be 1 divided by negative 8 centimeters minus 1 divided by 16 centimeters. Go ahead and type all that in, and you're going to say that 1 divided by the distance to the image is going to be negative 0.1875. Units will be inverse centimeters. Keep in mind that I've just left everything in centimeters. It's going to give me my distance to the image in centimeters. Go ahead and invert that guy. It's going to come out to be negative 5.3 repeating centimeters. The negative means that it's on the side with no light. Now if I'm interested in the image height, I know that the magnification is going to be the height of the image divided by the height of the object, which is also going to be equal to negative distance to the image divided by distance to the object. So I'm interested in image height, so I'm just going to move this height of the object up right there. Height of the image is going to be equal to negative 5.3 centimeters. Divide that guy by the distance to the object, which is going to be 16 centimeters. Let me go ahead and write centimeters up here. Now height of the object, that's going to be 3 millimeters. You can kind of see here, centimeters is going to cancel out. I'm going to have my height of my image in millimeters. That's going to work out to be about 1 millimeter. And now a problem with light slowing down as it goes through materials. It's going to be related to the index of refraction. Essentially, we know that the speed of light in a material is going to be the speed of light divided by the index of refraction of the material. So here I've got 3 different materials with 3 different indices of refraction. Let's just take a really quick look at the velocities. velocity is going to be 3 times 10 to the 8th meters per second divided by 1.36. That's the index of refraction. It's going to come out to be 2.21 times 10 to the 8th meters per second. Part B, same deal. It's going to be 3 times 10 to the 8th divided by 1.51. So we're going to get 1.99 times 10 to the 8th meters per second. For part C, I'll spare you writing it out again. It's going to end up to be 1.97 times 10 to the 8th meters per second. And a little bit of practice using Snell's Law. Here we have a diver who's going to be shining his flashlight upwards, and it says it's going to make an angle of 35.2 to the vertical. So kind of draw my vertical or my normal surface. So tell me this is going to be 35.2 degrees. I'm going from water, n is equal to 1.33, to air, n is equal to 1. So I'm going from slow to fast. I would expect this guy to bend outwards at a larger angle. So I would expect it to kind of go like that. And I'm asked for, what is that angle going to be equal to? So this is my initial, this is my final. And I know this is going to be my initial. Snell's Law. N1 sine theta 1 is going to be equal to N2 sine theta 2. I'm interested in theta 2, so divide both sides by N2. Go ahead and cancel these guys out. Take the arc sine or inverse sine of both sides. We're going to get theta 2 is going to be equal to the arc sine, inverse sine, of N1 sine theta 1 divided by N2. So it's going to be the arc sine of, in this case, 1.33 divided by 1, that's index of refraction of air, multiplied by the sine of 35.2 degrees. It's going to give me an angle of 50.1 degrees. That's larger than the 35, so I'm feeling pretty good about it. Okay, and a problem using lenses. So here I have a converging lens. It tells me the focal length. Because it's converging, focal length is going to be positive, so 215 millimeters. And I'm getting a sharp image that's 391 millimeters behind it, so there's my focal length. I can kind of go back a little bit further. So there's going to be my nice sharp image. And something to kind of remember here is that the distance to the image is going to be positive because it's on the side where the light goes. So the light rays are kind of going in that direction, so it's going to be a positive 391 millimeters. If the image was located to the left, then image distance would be negative. The object is always going to go on the left. So now let's do a little bit of ray tracing. Very tip here. Gonna work our way through the focal length and kind of come out parallel. I'm gonna draw one that goes through the center of the through the center there. I'm gonna draw one that goes out parallel and kind of cuts through the focal length. Not really the best scale I have here. So that's going to be where my object distance is. So I would kind of expect it to be larger than the focal length. So calculation, I know I have one equation, 1 over distance to the object plus 1 over distance to the image is going to be equal to 1 over the focal length. So 1 over to the distance of the object is going to be equal to 1 over the focal length minus 1 over distance to the image. So 1 divided by 215 millimeters minus 1 divided by 391 millimeters. Type all that into your calculator. You're going to get 1 over distance to the object is going to be equal to 0.00209. Some more decimal places, just keep them. Go ahead and invert that in your calculator, and you're going to get the distance to the object, 477 millimeters. So my drawing really wasn't to scale, but it was larger than the focus. One thing to kind of keep in mind is that the distance to the object pretty much always going to be positive. The real question is when is my focal length negative? That's going to be when it's a diverging lens or convex lens. And where is the image? If the image was over here, then the distance to the image is going to be negative. image is over here, distance to the image is going to be positive.